Okay, hi, thank you all of you for being here. We will present our work on detection of cryptographic algorithms by the analysis of control flow graphs using the grap tool we developed. So let's introduce ourselves. So I'm Leonard Benedetti. I worked with Aurélien at Airbus to develop this tool, and I'm an engineering student at ESIA.
So I'm Aurélien Thierry. I work at Airbus Cybersecurity as a malware analyst. So, as Leonard said, the topic for us today is the detection of cryptographic algorithms. So we will look for them in programs. So it is useful for us and for analysts in order to save time so that you can automatically know which programs uses which algorithm. And we will apply that, we usually apply that to malware analysis. So this year and the past years have been marked with a lot of ransomware attacks. One thing that is notable about ransomwares is that they massively use modern cryptography. They will use symmetric crypto for file encryption, and they will use asymmetric crypto for key management. So they will also use a wide range of ciphers from AES to RC5 to many others. The aim for the kind of system we want to design is threefold. The first thing, if we want to have an automated analysis platform, we want to have automatic answers about programs. I will give it a binary and I want the system to tell me, okay, this program is using AES, for instance. If we want to help reverse engineer, we will need more precise information. For instance, within IDA, we can say, okay, this function is implementing this cipher and so on. And also, if we want to extract cryptographic materials such as encryption keys, this kind of system can also be useful. So we're not the first to tackle this kind of problems. The main used approach for crypto detection is through constant detection. So you will look in a binary and look for hexadecimal patterns that are constants of the algorithm. For instance, for AES, you will usually find the S box that is always the same. You also have tools such as Yara that work on byte level matching. So you will have a signature that is looking for strings or for regular expression on hexadecimal values. So the very good thing with this approach of constant detection is that it's very quick. You don't have to dive too much into the semantics of the algorithm. And the problem is that you will find some algorithms, such as RC4, that don't have constants, and it's difficult to make patterns for them. Also, if the constant is modified, for instance, there are some malware that use AEX with a modified S-box, then your constant detection system will not work. On the other hand, we have more high-level approaches that work with function evaluation, such as Sybil or Aligo. So the thing is, these systems are very precise. They will work by having, on the one hand, a function of an unknown binary with a function to identify, and on the other hand, non-functions that you have implemented. You give the same inputs to the malware and to the function that you know, and if you have the same outputs, you will be able to identify which algorithm is used. So this method is very precise, but it's slower because you need to evaluate the functions at some point. Again, if the algorithm is changed, you will not detect what you wanted to detect, but the thing is, it's a less important problem than with the constant detection. Our approach, our aim, was to have something that is between the two, that would be able to work on the disassembled instructions and on the control flow graphs of the binaries. So that's what we will talk about in this talk. So the first example I'm going to take today is the one of SHA-20. So it's a modern stream cipher that is quite reliable and quite secure. I will take a known implementation, such as the one in LibreSSL. So this is what you see on the left here. So what is notable about SHA-20 is that it uses a scheme of ARX. So that is three operations that are the addition, the XOR, and the rotation. So if you look at the pattern at the implementation, you find these instructions. You find the add, the XOR, and the roll, and you also find some instruction to move memory, which is move. So the pattern you will look for is something with an add, a XOR, and a roll, and as you can see, it repeats itself multiple times in the algorithm. So the first thing I want to show you is how you can do that with grap very easily. So I have a first demo somewhere. Okay, so here I have one, yes, we can see it. I have one binary which is compiled with GCC and which is libreSSL. So I will write my pattern. So as I said, you want to find an add. Then if you remind, it was a move, but the move is not really interesting. It is not in the IRX scheme, so I don't care what instruction it is. Then I want a XOR. Then I want a roll. And I will find that on the binary that is here. So the first time I launch it, it's a bit slower because the disassembly needs to be done, so it takes around 10 seconds. And then we will see all the matches that are found within the graph. Okay, so as you see, there are 64 matches. And what grap says, we have a little information about the file at the beginning, so it's quite huge. It has 300,000 instructions. We found 64 matches. And for each match, you have the addresses of the instructions on each instructions. As you can see, we were looking for add, XOR, roll, so that's what we find here. So that was a first way to detect this kind of very simple pattern with grap. As we saw, you can define the pattern on the command line interface. It's quite useful to prototype patterns. Once you've done that, you can inspect the pattern that has been generated and modify it for further needs. So this works for very simple patterns. For more complex ones, we wanted to have something visual. So we worked on an IDA plugin that is able to, where you are able to select the instructions that you want in your pattern. So I will show you that now. Up. So here I have libreSSL. So I'll be looking for Shasha. So it is compiled with symbols, so I can find the function Shasha encrypt bytes, and I will try to make a pattern. Okay, so if I scroll, up. Okay, so here we have what we were looking for. So the pattern is add, XOR, and roll. I have the IDA grap plugin here, where I will create my pattern. So I want to add the first root of the first node of the pattern. Here, set root node. Then I will ask some more. I want the XOR instruction, for instance. So you see on the left panel, you almost see on the left panel the pattern that is being generated. I want to go until the second roll, and I will show you the pattern. Okay. So, okay, it follows the dot format. So our patterns follow the dot format. You will have the name of the pattern, and here the first pattern we create by default, it matches exactly the instructions that were in IDA. So we are looking, the first instruction is an add, with its first argument is here and the second argument is here. Okay, it's the first pattern, but it's not very useful because if you change anything, it won't match. So we want to make it more generic. So I can ask for more generic arguments. So we will only keep the opcodes. You cannot see, but it's add, move, XOR, roll, etc. Then I will also want to remove the moves. As we saw, they were not really useful. So I can ask to remove them. And I can also ask to factorize the instructions. If I have like 2 moves in a row, maybe there is some other implementation in which there is 3 moves or 4 rows or 4 moves. So I can ask for factorization. So I will zoom again. So that is quite easy pattern. So as we saw, there is the add, the XOR, roll, etc. It's repeated twice. At the beginning here, you have the nodes, and here you have the edges. So the nodes have names, and then you say, okay, this node is connected to this node, etc. So now I have created my pattern. I can name it. So this is RRX on LibreSSL. I can save it to some file. And then I want to match it against this binary. So this is LibreSSL, so I should match this function and maybe some others, so I can launch the detection. It takes some time because, as I said, this binary is quite huge. When we match, we parse the whole graph in IDA. Typically, on a normal binary, like on a malware, it will take less than 1 second. Here it takes 30 seconds, yes. It should be finished soon. Okay, so we have the matches. So here we can see the instructions, the addresses of the matches, and the name of the functions. So we find again all the functions we are in, Chacha encrypt bytes, and another one, Chacha encrypt byte 0. Just for being user-friendly, we added a way to color the matched patterns. So if I ask for color, I see that the loop I was looking for here has the pattern repeated many, many times. So it's almost always this pattern that is repeated here. Okay, so back on the slide. Okay. Okay, so what we saw in the IDA plugin is that we can select the interesting arrays directly in IDA and create a first pattern. Again, this will usually not be your final pattern because you want it to be more generic, but it's a good way to begin. So for Chacha, I can have a more generic pattern here. So that's what we saw already. So this follows the dot format. You have the name of the pattern here, and you have a bit more generic things like the add here. You want it to be able to repeat. Maybe there is one add, maybe there is two, etc. The move, there can be 0, there can be 1, or there can be more, etc. So we've seen a bit how our graph works. Just I will make a point on what is a project. So it is being mostly developed at Airbus Cybersecurity. So as we saw, there are many ways to define patterns. This is to be more user-friendly. So we have easier command line interface patterns here. You can save the file to save the pattern to a file and match it. And then software-wise, grap is three things. You have the command line interface, that is a standalone tool with a disassembler. You have the IDA plugin, and you have Python bindings if you want to use it in scripts. So a bit of algorithmics. The main problem we tackle with grap is subgraph matching. So the problem is how to do that quickly. We use the fact that control flow graphs are very specific graphs. Exactly, you cannot exchange the orders of the children of a node. For instance, if you have a call instruction, so you have a call instruction here. The thing is, we define that it has two children. The first child is the next instruction, because at the end of the call, you will return to where you were. So you will execute the instruction at the following address. So that is the first child. Then the second child will be the remote instruction, that is the function being called. So you have two children for call, and these two children cannot be inverted because they do not seem the same thing. They are very different. So we have children that are ordered. The other property is that on x86 you will only have at max two children for a given node, because on call you have two children, on a conditional jump you have two children, for instance. So with these restrictions we have an algorithm that is quite fast. If you want more details, you can look for it in the paper. Again, about the grap project, it is something that is available online. You can we used it for malware detection. We used it against malware families to create, to do some classification and some feature extraction. And we tried to make it the more friendly to use as possible. So we support the latest IDA 7 and then some legacy versions. We have precompiled binaries for Windows, and the build process for Linux should be quite easy. You just have to install some packages and use CMake.
Okay, so now we'll see with Aurélien how to create quick patterns. We will see how to create a specific and generic graph pattern to detect cryptographic algorithms. To do so, we will take an example with the AES cipher. So, AES is a cipher designed at the beginning of this century, absolutely ubiquitous nowadays in many protocols and everywhere you want. We will quickly return to its operation. So it's a block cipher with one function executed multiple times. So the first step is a key schedule, which is necessary to derive from the master, the secret key of the algorithm, one keys which will be used accordingly around at each round. Then the core of the algorithm begins, which is the first step is add one key, which allow to merge the one key to the current state of the cipher. So with a logical disjunction, which is XOR. Next, we will have the subbytes. So the encryption rounds will begin. There will be between 10 and 40 rounds according to the version of AES you will use. So this step, subbytes, we will pass. So you will represent your state by a 4x4 matrix. So with 16 bytes, you will pass each of those bytes by a substitution box. So each byte will be replaced by another one. If you want to know where comes from this substitution box, it's in fact the multiplicative inverse inside a finite field known to have good linearity properties. So next step is shift rows, which is a quite simple step. You will just rotate each row, so the first one won't have any shifts, and 1, 2, and 3. The mixed columns step is maybe the more complicated one. So this time we will consider that each column of the matrix is a polynomial, and we will multiplicate the polynomial by another one, a fixed one, modulo something, and the coefficient of the result will be used to get our next step. All of those operations will have two properties. The first thing is to add some confusion to the algorithm, which is a way to decorrelate the ciphertext at the end with the input and with the key. And we will have diffusion, which is also known as avalanche effect, to do that bias in input won't be in the output. So as we see, the algorithm is quite specific. The structure of the algorithm is really something specific with a round function. Then at the end, the last round is exactly the same, but without the mixed column step. There is some specific instruction like rotation in shift rows that are always there. And the arithmetic in the finite field in mixed columns should be also quite specific. So now we will see how to effectively create a pattern with grap. The first thing to do is to choose one implementation in particular, because for same cryptographic algorithms, you could have many implementations which, for example, can address some different constraints, security features if you want to avoid some side channel attacks. You could also minimize the time cost or the memory footprint. So for AES, we chose LibreSSL because it uses the same implementation that OpenSSL, which is ubiquitous and very, very used nowadays. So let's take LibreSSL and we will compile it. We will compile it with different compilers because each of those will function, will have an internal working different and produce different assembly code. We will enable different optimization levels to get different transformations. For example, optimization could be loop unrolling, arithmetic simplifications, code rearrangements, and so on. And since we want to support both 32 and 64 bits, we will compile on those two architectures. Next, the most important and the most time-consuming step will be the assembly of the code produced by the compilers, and we will search for invariants. That is to say that we will look at the code compiled in different contexts, compare them, and try to identify some parts that are not changed across all binaries. So on one hand, you will have the structures, so that is the topology of the control flow graphs, and look if there is some common things in all of those graphs. And on the other hand, we will look at the meanings of the instructions, of course, and try to see if there is always some instructions that are there, even if optimization and other transformations. And then we will begin to write a pattern and try to, of course, match the reference implementations. And we will also test it on real-world binaries to measure and to adapt it, to generalize them, and be able to detect the most implementation as possible. So here we are, our final pattern for AES in a graphical way. So we can see that, first of all, the structure of the pattern is quite similar, almost the same, that AES. We have an initialization phase with a big loop. So this is the transformation we described earlier. Then here you will have the condition to check whether all rounds has been performed. If so, then the algorithm is over, and else we will continue and loop on it to continue the transformation. So you can see that on the semantic meanings of this pattern, it is mainly arithmetic and logical operations that are searched, mainly shift, memory handling operations, and XOR 1. Here you have an extract of the assembly code of binaries that implement AES, and you can see the logical and arithmetical operations that perform the mixed column step described earlier, which is a specific arithmetic of polynomials in a finite field. And at the end, we will have some specific binary masks to extract the final steps, the final state. So, about the results we obtain with this pattern. It works on the reference implementations. It is quite interesting because we do not rely on any constant detection, like the S-box, for instance. So we know for sure that some malware in the real world have already changed the S-box to avoid detection, and of course we are not impacted by those kind of manipulations. It is strongly based on the structure in itself. It is really about, if you have a match, it's because something in your binary have a very, very similar structure to AES, which is quite specific. And it's interesting because even if it's not AES, it could be another algorithm which uses a subset of AES or anything else. It's quite interesting for the analyst, and it is a desirable behavior. And finally, we also trivially support the hardware acceleration with AES and I, which is just some specific instructions we add to the pattern to detect them easily. So what about the difficulties and limitations? But just before that, a little demo about AES. So we will look at the pattern. VIM for the win. Okay, so here we are our pattern. You can see that you have the different blocks we presented earlier. If we scroll a bit, you also see another pattern for exactly the same implementations, but more compact. In fact, LibreSSL provides two implementations, and one is a bit more concise. So it's exactly the same, but just with a little less operations. So we match it also. And finally, the very, very simple pattern to match AES no instruction, just search for specific OP codes. Okay, so tests. So we will search for all of our patterns on binaries. Okay. The quiet option to just have one line per detection. So here we are. We can see that on libsodium, the grap detected just with ARX the new instruction of AES, which makes sense because libsodium does not implement AES softwarely, but just use an hardware version. So get back to the slides. Thanks. So now the difficulties and limitations we encountered with the design of cryptographic patterns. In fact, this approach is not applicable to all algorithms. It is always possible to develop one pattern from one algorithms, but if you want to make it generic and be useful with many transformation of compilers, you will have to rely either on the structure or to the semantics of instructions. On some algorithms, like for instance SHA-1, it's complicated because the structure is really simple, just one loop and one function, very simple, with classical arithmetic that can be carried out by compilers and optimized in many ways. So in this case, it won't be possible easily to make generic patterns. So you have to have at least some specific characteristical properties. The cryptographic code can take many forms. You could use it with a specialized instruction, as we say. Another interesting thing is the vectorization. You could use specialized operation like AVX to implement it with using some specific registers to use vectors in a performance goal. For this kind of implementation, it will change deeply the architecture of the structure and the semantics. So if you want to support those kind of implementations, you will have to develop a specific pattern. The ciphers could be used in other algorithms directly. For example, if you want to implement AES with a mode of operation, like for example, say CBC, you will implement both at the same time, and the structure could be eventually modified, and the pattern could have difficulties to detect it. And nowadays, operating systems provide cryptographic API, like a crypto API for Windows, and binaries that use it. Of course, we can't detect the cryptographic code because there is no cryptographic code, but you could detect the call, which all other tools do that, but it's not in our scope. And finally, if you want to design and conceive some generic patterns for cryptographic code, it will take some time because you have to look to the algorithm and study the implementations. So it won't be as easy as just list the constant used and try for third gem. So let's discuss now a bit about this approach. So here's the command we just typed in the demo. The same results we already commented. It's quite fast, 25 seconds for the whole thing, and the disassembly, which is a one-time step, you done at the first launch of the commands, and it's already done. And the matching is very, very, very fast compared to the size of the binaries we used. If you have some malware, it will be faster. You can see that on different contexts with different compilers, it's quite fast, no matter optimization level you use. Okay, so now let's get back to Aurélien.
Yeah, so what we wanted to do next was to match our patterns on real-life malware. So we did a quick analysis. So this is still a work in progress, but we took some malware that are some ransomware and some rats, and we tried to see what we could detect. So the first thing we have here, 10 malware. I took something like 10 samples. It's not a lot of samples. So as Leonard said, on malware, it is much faster. So for 10 malware, 10 samples, it takes less than 3 seconds for disassembly plus matching. And the results are the following. So for instance, the Sage ransomware, it uses SHA-20, and it is implemented directly in the binary code. So we were able to detect it with the IRX pattern. We also found some malware like Ramsex that use RC5. RC5 is a block cipher that also has an IRX scheme. So we were also able to detect it with the same pattern. Then the following are some malware, and we have a lot of binaries that use the hardware version of AES, which is AES-NI. So with the very, very simple pattern we wrote, it's very simple to detect them. Then, as Leonard said, the problem with AES is that most modern malware don't implement it. They will use Windows Crypto API, so there is nothing for us to match. So our approach won't be useful in this case. Then we had some malware such as Pythia and NotPythia that are using SALSA-20. SALSA-20 is also an algorithm that uses an RX scheme. But the thing is, in this case, it was obfuscated, so the pattern didn't work. So overall, we found that in this small study, the RX pattern seemed to be useful, and for the AES one, the problem is that malware usually have dynamic calls to crypto API, so the pattern did not match. Overall, our approach is tries to be different, so we try to be between byte level analysis and algorithm level analysis. So we really are working on the implementation level, so on instructions and on control flow graphs. We have the same problem as the other approaches, since our object is the implementation. If it's changed, or if the control flow graph is specifically obfuscated to not match the pattern, then of course we won't have any detection.
So, conclusion time. There are some advantages and disadvantages. It's quite quick, it's quite fast. You could use it to detect implementation without relying on constant detection. You could use it as an analyst to define quickly some very simple patterns and check if they are found elsewhere using the IDA plugin, for example. And you could also use grap in script or with a rules system to detect, for example, and classify family malware, for example. On the dark side, it is not always possible to define generic patterns. You could just do for one implementation and which does not support any complicated transformations. Creating a generic pattern can take a while if you want to make it generic, and if you are in the situation where an active attacker wants to avoid the detection, it won't be complicated at all. They could add some Mongo Jumbo instructions or just obfuscate the structure, and it won't work anymore. So it's functional, it's useful, it works. You could create patterns quite easily. It will be a little bit longer if you want to make it generic. It's open source. You can share it, enjoy it, fork it, and pull request it. In the future, we want to add more generic patterns for algorithms, for example, with asymmetric ciphers, maybe some hash functions. We also want to push our study further on the quantitative, to perform some serious quantitative analysis, to have a correlation matrix and a detail about the false and true positives and negatives. And we also want to add some interesting features, like, for instance, the meta patterns, which is all, instead of matching for specific instructions, matching for subgraphs with some logic behind it to make the patterns smarter. Thank you very much.
So we got enough time to take a couple of questions.
Is there a way to create automatically patterns? For instance, you take a known implementation, you extract the control flow graph, and from that you try to define a patterns that recognize this and then would recognize some similar implementations?
Yes, you could use the plugin just to create quick patterns and match for implementations, but for ARX, it's quite easy because the pattern is really simple. But if you study some more complicated algorithm, like AES for instance, it will be more complicated because you have to define which specific parts will be common in a different version compiled in different contexts. So if your implementation is simple enough and the use of optimizations levels in your compilers does not make any change, it could work. Yes, absolutely.
Any other question?
You publish the code of grap. Do you publish your database of patterns?
Yes, absolutely. It's on GitHub.
So there are only so many algorithms and way to obfuscate them. Is there any hope that by a lot of efforts the database is full enough so that we can detect sufficiently many things?
Let's hope for it.
Cross a finger.
Pull requests are open.
Did you try on public cryptography, RSA or something else?
In fact, it's an interesting point we want to push further. There is, in particular, I think, to elliptic curves cryptography, which implement some specific mathematics with the derivation of elliptic curves. And for now, it's a bit more complicated because for the elliptic curves, it involves floating points, so the transformations are a bit more complicated. But for AOSA, it's integers, so it won't be too much complicated. So yes, it's in our perspectives. For now, we just looked at symmetric ciphers and hash function because it was in a ransomware for ransomware at the beginning, and the most critical part reside in file encryption. But yes, absolutely, it would be great to test it with public key cryptography. Thank you.
Okay. Any other question? No? So we're going to be thanking again Leonard and Aurélien.